So today we are going to be looking at sprites and palettes and pixel data of images. This is the lecture for today. And the to-do list for today is to edit a palette somewhere in the game and then change a sprite somewhere in the game. And we'll be learning how to do that. And then once you do that, then make a patch with ellipse and then send your patch in the Discord with a description of what you changed. So very similar to what we did last week, except this time with sprites and with palettes. And yeah, so make sure you download the starter files that I prepared. So the first question is, how do computers like store colors and store pixels? And the answer is with RGB values. And RGB stands for red, green, blue, so RGB. And it's made up of like a 3-byte number, and it's 3 bytes, one for each color. So this is the red color, this is the green color, and then this is the blue color. So this, so we can see, like, if we slide this around, like if we have it be like really red, then our red number is going to be really high. If we slide it to like the green, then our green number is going to be really high. If we slide it to blue, then our blue number is going to be really high. And this is the fundamental way that computers store data, is with this color notation of 3 numbers, RGB. And yeah, so RGB is like the way that computers store colors. And so now with this in mind, so if we pull up like a picture and we try like drawing on it, and then if we were to save this file and then like maybe like open it in a hex editor, what do you think we would see? Like, yeah, imagine you were the one who invented the PNG file format. How would you do it? Like, yeah, does anyone have like something in mind of like how a PNG file is saved? 2D array of RGB. That's a fantastic idea. Yeah. So 2D array, so meaning like you have just like a matrix, and every single element of the matrix is every single element of the matrix is like a different color, maybe like a 3-byte number, and then like the height and width of the matrix will be like the height and width of the image. That's a fantastic idea. And but in binary data, we can't actually store a matrix because like we don't know what the resolution is. So yeah, what are other properties that we need to probably store in this PNG file in order to like actually show that it's a picture? So a big one is resolution. We need to know the resolution. So we know like it's like 50 by 50. So therefore, like we know if we get 50 colors in a row, that's one line, and then the next 50 will be another line, and next 50 will be another line. So we need to know the resolution. Yeah, cool. So, and I think that's a pretty good simplification of like, of a good picture storing file format, is just you have the resolution, and then you just have a long list of all the different colors. But can anyone think of a problem with this? So one problem is, so look, we're only storing 2 colors in this image. It's just black and white. So we really don't need to have a whole 3-byte value to store all of the colors on this, right? Like if we were to store 3 whole bytes, like it's like, oh, like 100% red, 100% green, 100% blue, so therefore white. So FF, and we store FF for every single pixel going across, and then on the next line our FF, and then finally we get to like one point, and now it's 0000000. Like, oh my gosh, like we have to store so many numbers, even though it's a very simple image. So really, actually, what we could do is we could simplify this image down. Since there's only 2 colors, we could actually just use a single bit, just a 1 or a 0, to show like, is it white or is it black? And we could say like black is 1 and white is 0. So now, so before, like if we had maybe like a 50 by 50 image, so therefore it's I believe 2,500 pixels. So originally this would correspond to 7,500 bytes. If we were to store, if we store all RGB values. But we don't need to store all RGB values in the case of a black and white image. So we could just store, like, instead of 3 bytes per pixel, we could actually just store 1 bit per pixel. So so instead we could say, like, yeah, let's say if we store 1 bit per pixel, so now it's, yeah, 2,500 pixels to 2,500 bits. And if we divide this by 8 to get the number of bytes, so yeah, 313. So look at that. So we end up saving a ton of space if on this black and white image, if instead of doing instead of storing every single RGB value, we instead just store, like, black or white. So therefore, it is better, like, let's say, yeah, if we have a black and white image, it is therefore better to only use, like, 1 bit per pixel, just black or white, and we end up saving a ton of data. But now let's say, like, we store, like, 4 images, or I'm sorry, 4 colors. So let's say we have, like, this red guy, and then we also have this blue guy. So now we have 4 colors. We have white, we have black, we have red, we have blue. So in theory, like, how many different bits would we need to store like each pixel? Can anyone think? So if we have 4 colors, how many bits would we need? So if you have 4 colors, so let's write it out. So let's say we have black, white, oh no. Let's call this black, white, and then blue and red. So black, maybe we could say that this corresponds with 2 bits, 0, 0. White corresponds with, like, 0, 1. Blue corresponds with 1, 0. And then red corresponds with 1, 1. So now, if we use 4 colors, then now all of a sudden we need 2 bits per pixel. Does that make sense, everyone? Yeah. So now what would happen if we added a 5th color? How many bits would we need? Can everyone put in the chat how many bits we would need? Yeah, it would be 3 bits. The answers. Yeah, so if we had green, then all of a sudden we would need a whole nother bit, because then green would look like this. So now what would happen if we added a 6th color? Can everyone private message me how many bits we would need if we had 6 colors? Yeah, we would still only need 3. Let's say, I don't know, pink. It would be, yeah, 1, 2, 3. All right, so if we add another color like yellow, then it would be, I don't know, 1 or 1, 1, 0. Yeah, and then, I don't know, brown, 1, 1, 1. And now how many bits would we need if we had 9 colors? And yeah, and we would need 4 bits because gray. Yeah, so this might be like the code for gray. So this is actually how the PNG file format works, and how the BMP file format works, and how, like, the GIF file format works. Basically, like, all types of images that we're familiar with, all of them use this style of storing pixel data, where instead of using the full RGB value per pixel, they simplify it into this little table, which we call a palette. So, so it creates a palette of all these different colors, and it assigns some value to it. And then it makes a 2-dimensional matrix, makes a matrix of like what the image should be, where every single cell of the matrix corresponds with one of these values. And if we do this versus storing, like, the full RGB, then we end up saving tons and tons of data. And so that is actually how, like, image compressors work. is, yeah, wait, can anyone think now? I want everyone to think like, so how do image compressors work? Like, let's say you had an image and it had an insane amount of colors, like an absolutely absurd amount of colors, and it used up like almost every single color on this color wheel. Can someone, can you, you guys like try to private message me a strategy of how to, reduce the file size of this? Yeah, so if you have a file with an insane amount of colors and you wanted to keep the same resolution, but you just wanted to lower your file size, what could you do? Let's say that, so let's call this file large.png, and this is its palette. Now let's say like, I don't know, like black uses, yeah, so this is what black would look like, and like this is what red would look like, and this is what blue would look like. Yeah, so this is what the palette would look like on this hypothetical image. Is the palette, every single color is just mapped to its RGB value. So one strategy that we could take is we could lower the color depth. And lowering the color depth basically means just going and like reducing the amount of colors that are allowed. So it's where you say like, you know what, actually, we're not allowed to use the color black anymore. So instead of using black, we're actually just going to use really, really dark gray. Or you might say like, oh yeah, we're not going to use this white anymore. We're going to use this, yeah, really, really light gray. Or we're not going to use this red anymore. We're going to use like a slightly orangish red. And if we, yeah, so this is called lowering the color depth, or basically just removing bits from the palette. So you could just go and like just delete a bunch of bits, and now you've made each of your from your matrix, you've made your cell size way smaller. So now your file size is going to be way smaller. Like, so I guess on this image. So if we wanted, like, let's say I didn't really care that there was like red and blue. So remember, so we're using 2 whole bits per color for this image. But let's say I didn't have enough room for that. So what I could do is I could just say, actually, you know what, screw that. I'm just going to compress this file into using a color bit, or a bit depth of 1. So therefore it only uses 1 bit per color, meaning that all of the blacks and all the reds and all the blues might all get averaged out into like a gray color instead. So we basically just like take out some of the colors that we're allowed to use. Yeah, so like if you take this palette and we just say, actually, you know what? We're not going to use brown, yellow, pink, green, red anymore. Or yeah, actually, we're not even going to use red, white, or black. We're only going to use white and gray. So therefore, we can like delete that, and then now we can crush all of these colors down into white and gray. And so this will reduce our file size because now we're using just fewer colors. So now the amount of bits that we need to use per pixel is lower. And this is how image compressors generally will work. And like if we were to go and actually try to save this image as PNG, save. So here we can actually see, so bit depth. So we can actually select the bit depth on paint.net. So it's saying auto detect, but let's make it actually 1 bit. So if we select that, now look at that. It actually reduces the number of colors used. It uses gray and it uses black, like exactly kind of what we were having it be here. Or instead of 1 bit, maybe we could have it be 2 bits. And now we see that this is actually what the image looked like. And like if we wanted, we can make it 4 bits or 24 bits, or yeah, so 24 bits, this is RGB. 32 bits, this is even greater than RGB. This is what like fancy OLED TVs will do. But if we keep it at 2 bits, then that's good enough and our file size is manageable. But what's very, very important to hear, what is very important to understand is the concept of palettes versus pixel data. They're completely separate. There is the palette data, which stores just like which colors are being used and then maps them to some binary data. And then there is pixel data, which is just a 2D matrix of a bunch of different of these pixel datas. So like look, like green, like this does not at all correspond to its RGB value in computers. However, we've just mapped green to this value. So anytime that we see this value in our binary file, like if we were to open up this file in a hex editor, anytime we would see 0100, we know, okay, that's a green pixel. Or if we saw 0111, that would be a brown pixel. Yeah. So, and this is actually the way that Super Mario Bros. Works. So yeah, we can see here. So here's Toad. This is actually Super Mario Brothers 2, but don't worry about that. So we can see, so the NES actually only uses 3 colors. And one of the colors, or technically 4, but one of them is just a transparent color. So so that allows the pixel data to have a bit depth of 2, because only 2 bits are used. But then elsewhere, there is a palette table where it stores them, like the remapping, the pixel data to actual color data. So yeah, so we can see like that this color, anytime we see 1 here, it corresponds to to this color. And like, yeah, we can scroll down and yeah, and then, so this is actually like how it's stored. So we would see, if we're going to look later in the ROM file, and we'll see that anytime that we have 00111100, so this is a 1 byte, remember, so bytes are 4 bits. So we have bytes are 8 bits. So we have 1, 2, 3, 4, 5, 6, 7, 8. So this chunk right here is 1 byte. So anytime we see a byte with 00111100, we know that it's going to be this shape. Yeah. Or if we see like 11000011, then we know it's going to be this shape. And but the way, like, let's say we wanted to make now like a purple heart, we wouldn't change any of these 1 zeros at all. Instead, we would go to the palette, and then we would go and change. And we would change the remapping. We would say, yeah, so 10 actually isn't red anymore. We're going to change that remapping to purple. So now anytime we see 10, it actually means purple. Yeah, so that is how like image files work. So that's how like PNG works. That's how GIF. So they're called raster graphics. Yeah. So raster graphics as opposed to vector graphics. Vector graphics are like maybe like for example, like a font is a vector graphic, whereas a raster graphic is when you have pixels. So raster, I think pixels. Yeah, BMP file format, and we can look up palettes. Yeah. So and then we can learn all about paletting. So paletting is when you just store the palette separate. Yeah. So here we can see. So here is this thing of strawberries, but then here's actually all of the colors that are used. So it's not actually all that many colors, even though it's a fairly like colorful looking image. Like you got reds and yellows and all these nice colors, but we can just condense this down into this many colors. So now our color depth is actually fairly low because we're only using this many colors. Okay. But the NES does not actually use RGB values. The NES uses its own color system, and I have it right here. So this helps in a few ways. It helps with the PPU, the picture processing unit. That way, it doesn't have to handle these large 24-bit numbers. That way, it only needs to handle these 8-bit numbers, because the NES is actually 8-bit. So our computers today are all 64-bit. However, the NES was 8-bit, so it was very simplified, and getting intense colors just like wasn't possible. So unfortunately, the NES was limited to just these colors, just because the PPU and the CPU just could not take it. So yeah, here are all the different colors. So so instead of having like for example, like blue is supposed to be like 000000FF, but instead we just have it be like 01. So yeah, this is just the reduction of the NES's colors. And then here is an example of what the pixel data could look like. And so I could have made this any color, but I chose to make it Mario's regular like colors, but I could have made it any color. I'm just trying to show you the pixel data. So yeah, here is actually how each of Mario's like little like subchunks are arranged. And each of these subchunks are called sprites. And sprites are basically just little chunks of pixel datas that are all scattered around the ROM file. So yeah, in the ROM file, if you were to open it up, you wouldn't just have like full pictures of Mario. Unfortunately, the NES had to do quite a bit of compression, so it will store all of the little, we call them sprites or like sub-sprites. We store those individually. And then we put them all together like this into a meta sprite when we actually want to draw Mario. So it is not possible to go and edit Mario directly. Instead, what we have to do is we have to edit these sub-sprites. And then once the PPU actually goes and assembles all of these sprites into a complete image, it will then use our new sprites that we put into the game. So, so that is what a sprite is. A sprite is just like a tiny little subchunk of a picture. Yeah, so like imagine like this image, we can consider this like a picture, but then a sprite would just be like a little subchunk of it, like this. Now, this is kind of weird, right? Like, why don't we just store the whole image? Can anyone think of the reason why storing sprites is a good idea? And yeah, go and like private message me, or you can put it in the chat, like normally, or speak up. Why would we want to use these subchunks versus actually storing the full image? Ooh, so you can only specify color depth for each sprite. That's a really good point. Yeah. So like, let's say you wanted to have the top half of Mario be blue, but you wanted to have the bottom half of Mario be red or something. So therefore, yeah, so you could apply a palette to each sprite individually. And that's true. Yeah. So Robin says that we need to save space. Also totally true. But how does doing this save space? Because it doesn't really look like it saves space because we're still using all the images, all of the sprites. So, but you're totally right. So can we think of like how, ooh, yeah. So Robin just said that we need to mirror images, or we can mirror images. Because yeah, look at these two sprites. What can everyone like look at them and so what property do they have? They're mirrored, right? So what could we do when we assemble Mario? Like, do we even need to have this sprite? Like, let's say we took out that sprite. What would happen if we tried to assemble Mario?
Be Mario without an abdomen.
No.
What?
So if we only had one of these sprites,
we could mirror it, but
exactly, and that's what the NES does. Yeah. So like, look at these two boots; they're identical. Why do we need both of them? We can just mirror it. So now we save 16 extra bytes, because I believe each sprite takes up 16. Yeah, each sprite is 16 bits. So if we just mirror some of these sprites, then yeah, we save a ton of space. In Mario sprite alone, yeah, look at that. We save 32 bytes just like that. But now, I don't know, let's say, okay, so this is the Mario facing right image. So how do we make the Mario facing left image?
Well, we flipped left the first four pixels. No, not pixels, sprites.
Yeah. Yeah, exactly. So that's crazy. So instead of storing like Mario like looking this way and then storing Mario looking this way, all we have to do is just store like his little like subchunks, and then we just change the way that he's actually arranged in the PPU. So that is the benefit of using sprites, or yeah, subchunks or subsprites versus using actual like full images. So yeah, when we go and edit the sprites in the game, so yeah, we're editing sprites. We're not editing the pictures or like the full Mario thing. We're editing the sprites. And by editing the sprites, we are editing yeah, we are in turn editing what the image looks like. But in the next class, next week, we will be learning how to edit how the sprites are actually arranged into a complete image. But this class is all about just editing sprites. And sprites, so remember, sprites are just pixel data. And but then we also have palettes. So we have palettes and sprites. And this is how the NES is made up of, palettes and sprites. And then another level is tile data. And tile data is how the sprites are arranged. And then like once you have tile data, then you have like meta tile data. And then so there's all these points of abstraction and of sub-chunking things, all to save space, because storing images just takes up so much space. So if we were to go and store, okay, yeah, let me give you an example. So if we load up Mario, yeah. So this is Super Mario Bros. If I were to take a screenshot of this game and store like all of the pixels in this, that's already a lot of pixels. So the resolution of the NES is actually, so it's 256 times 240. And if we pull out a calculator and calculate that, that's 61,000 pixels. So on the screen right now, there are 61,000 pixels. So if we were to go and store every single one of these pixels, let's say like we had 1 byte per pixel, at 1 byte per pixel, we've already exceeded the total amount of memory that it took to make this game. So if we look at like, yeah, this game's file, it's only 41 kilobytes. But the number of pixels, so the number of pixels on the screen right now is greater than the number of bytes used for the entire game. Like let that sink in. Like if every single pixel on the screen was 1 byte in the game's code, it would only go up to like right here. Like that's how big this game is. And yet there's 32 levels. There's music in it. This was considered like revolutionary for its time. And yet like we can actually visualize the number of pixels. Like that's just crazy to me. So the tons and tons and tons of abstraction and compression was needed in order to actually make this game work. We needed to have the sprites, and then, or we need to have palettes and then sprites, and then meta sprites and tile data and meta tile data, and like all of these levels. Okay, your homework for right now is to watch a little bit of this video, because I absolutely love this video, but I don't know if we have time. But it's actually, okay, well, let's watch like just a second of it. So I'll just like narrate it super quick. So here we can see like all of the available spots that you're allowed to put sprites into your game. This is someone who tried to make their own NES game. And so here's a boss that they're trying to put into the game, but the boss uses a lot of sprites. So yeah, we can see here that it uses a lot of different expressions, and it moves around. And so they're trying to put all of the sprites into the game, and yet they can't even fit all of it in. So they have to use advanced techniques to kind of like compress it. So yeah, so they take like the top part and they go and compress it by reusing the same picture. Reusing that guy. Can't reuse that, but then they take these last ones. Oh, okay, yeah, okay. Then he flips that one. Yeah, flips this one. Good, yeah. Wow, this like blew my mind the first time I watched it. He took like all of this data and then condensed it down into just 4 sprites. Yeah, really cool. So highly recommend watching this video. But so now, so now I actually want to show you. First, we're going to learn how to edit the pixel data. So I have tile. So here is Tile Layer Pro. This is in the NES hacking tools that I provided from last week. You can find it if you don't already have them downloaded. Sorry. And so we can just open up a ROM file. So let's open up vanilla. And so here is actually all of the game's code. So we can scroll down, and yeah, so it's using this like sort of encoding to get every pixel. So like this section right here is corresponding to yeah, so I guess so. It goes like 0, 0, and then blue, blue. So it'd be 1, 0, 1, 0. So this is, yeah, this like line of code right here is 0, 0, 1, 0, 1, 0, and then 0, 1, 0, 1, and then 1, 1, and then the blue is 1, 0. So yeah, it's really hard to read. Like if you wanted, you could try to like write the code in this way, but it's just displaying the code corresponding to the pixel data as if this was actually looking at pixel data. But if we go and scroll down, look at what happens. Wow, we can actually see the sprites in the game. So this is all the pixel data. And so notice the colors are super whack, and that's because it's just using some random palette that it came up with. So we can actually use this palette editor. This really should be called like a palette viewer because you're not editing the palettes, you're just like viewing what the palette would look like. So we can slide this along and like make our own sort of, we can look at like whatever palette we want to. Yeah. Yeah, so now we see like Mario is like looking purple. Oh, okay. And then so once we find our palette here, then we have to go up into palettes and click transfer to arranger. And then now we can see the palette up here. And there we go. So that's Mario. Yay. Yeah, and if we want, we can like edit the Goomba. And the way we edit is with this thing right here. So this is called a tile. This is called the tile editor, but really it should be called like the pixel data editor, because then we can go in and just like start drawing on it and put in our own little like decoration. Give them like horns. Yeah. Yay. And so now if we hit save, this will actually appear in the game. But I will not hit save because this is my vanilla version of the game. But let me make a copy of it. Oops, okay. So now that I've made a copy, I'll open edited. And now what I can do is actually open up another file. So I provided a file called sprites.nes. And now it has these sprites as well that I created. So, and then we can actually go into palette and then load. And I created a palette file for us to use. So palette, load. Yeah, so now it's using this palette. And now it's really easy to edit the Goomba because now he actually looks like normal. Let's okay. And now we can take this this Zelda sprite that I made, and we can just go and slide it onto, we can click and drag them onto the Goomba. Like that. So yeah, this is a really nice program because we can like copy sprites into other games. And then here I have like this Zelda squish sprite. So let's go and add Zelda squish. I can never find it. Dang. Okay, I can't find it. That's okay. Yeah. Okay, so now, yeah, we go and save this and open up the game. And it takes a second. Yep, okay, he's moving. And then there's Zelda. Yay. All right, and next I want to show you how to edit the sprite. So, or not, I'm sorry, not the sprite, the palette. So, boom, yeah, we edited the pixel data or the sprite. So yeah, let's open this back up in the emulator. So yeah, you want to take your game, open it in the emulator, and open up, in debug, you open up the PPU viewer. And in the PPU viewer, we have all of the sprite data or all the pixel data. And then here we have all of the palette data. So once again, like they're very separate. We have the palette data and the pixel data. And so here we can actually see this is the palette that's used for Mario's sprite. We have like this red and then this like skin tone and then his overalls. So 16, 27, 18, 16, 27, 18. So it's really hard to like to just be like scrolling through the game's code and figure out like, oh, okay, this is actually where the game like loads in the palette data. But what we could do instead is just say like, okay, so anytime that the game's code like has 16, 27, 18 just all in a line right next to each other, then that likely means that that's like where Mario's palette is. And these numbers are coming from this right here. So we can see like, so 16, 16, 27, 18. So these are the three colors used for Mario. So we can open this game up now in Goldfinger, which is the hex editor. So if we search, I always do. Search for, 16, 27, 18. And now search. Look, we actually have pulled it up right here. Cool, 16, 27, 18. So let's change the sprite. I don't know. Let's change it so it's 16, 27, 18. Let's change this 18. Let's make his overalls blue now. So if we look at here, so it looks like 10 is what blue is. So 16, 27, 18. So let's change this 18 to just 10. And then let's also make his red overalls. Let's turn them like, I don't know, green. Let's change it to 2A. So let's change 16 to 2A. So right here, so 16, let's change it to 2A. So in theory, maybe we have edited his palette. So let's go and save it. So we just saved it, and let's reload this game. Yeah. Look, and now, wait.
Nice.
I don't know. I think I messed up his. That's weird. Anyways, yeah. So now we edit his sprite, and you can like play around with it and try changing different colors. I will say though, so if we search one more time, so we searched for 16, 27, 18. But if we search again, then something else comes up. And if we search again, something else comes up. And if we search again, something else comes up. So there's a good chance that if you go and like edit the values, it may not actually be the sprite that you're looking for. Like let's say you wanted to try changing the like the Goomba palette. So looks like here's the Goomba palette, 3617-0F. If you go and like try editing that, it may actually not be the palette. It may just be somewhere else in the code where they happen to use 3617-0F. So it's kind of a trial and error thing. Kind of have fun with it. Go and try to change around a couple palettes. Go and try to change around the this pixel data. And then once you're done, go and put it into Lips and put your fancy hack into the Discord where we can all oogle at it and be proud of you. Okay, so I want to show you one more thing. So for editing palettes, we can look up, SMB1 ROM map. And a ROM map tells us basically what all the addresses are in the ROM file of everything. And like, yeah, we can see we can see the palettes. So the underwater palettes, like the seaweed and entrance of pipe, is stored at this address. Or so characters, we can see, so color of Super Mario. So we see that it's 5E8. But if we go on the class website and go here, so here I actually have the address loaded up of Mario's sprite, or Mario's palette. We see 16, 27, 18. If you remember that was what Mario's palette was. And here, you can see 5E8. And that is exactly what this guide is telling us it is. 5, oh no, now I've lost it. Characters, 5E8. Color of small Mario's hat plus outer clothing. 5E8, right here. So if you want, if you want, and you don't want to like go and manually go and search through all of the different Mario's, or all of the different like values that share the same value of the palette, you can actually just go on this guide right here, and I'll send a link to it. And it's on the class website in a few places.